Okay, well, coming to you from the NCTM conference in Chicago, sitting in the food court here for a little break, and thought I would make a part of the lecture here on the end circle, which is our chapter 2E in Math 439. All right, well, let's get right to it. What I'd like to do is give you, this first video about characterization of the angle bisector, and then how it relates to the end center, the end radius, and the end circle. So we'll try to hit these first two bullets in this video. So let's first go right into it. What's the characterization of the angle bisector? Well, it turns out that the angle bisector can be thought of as a set of points that are on the interior of an angle that are equidistant from the sides of the angle. So you might have never thought of it that way, but it turns out that this is a biconditional. If you're on the angle bisector, you're equidistant from the sides of the angle, and if you're equidistant from the sides of the angle, then you're also on the angle bisector. Let's see what that means in GeoGebra, just to get a good sense. So what I've done here in GeoGebra is drawn in an angle, just an arbitrary angle, ABC. It's dynamic, so I can grab A or C and change the angle, or B and change the angle. But we'll be measuring the angle ABC, or thinking of the angle ABC and its angle bisector. There is an angle bisector tool that's over here under the perpendicular line tool. It's the fourth drop down. You have to name the angle in a clockwise fashion. So I'll go C, B, A, and it'll throw the angle bisector in. Since I don't want to sort of confuse it with the angle that it's bisecting, I'm going to change its color. So I'm going to highlight that, change its color to red, change its line style to, let's say, a dotted line. And now it's kind of fun to just play around with the angle and the bisector and see sort of what occurs. You can see that the bisector, of course, moves when I move the angle and when I move the vertex of the angle, or either of the two, I guess, rays that determine the angle. But according to the book, if you're on the angle bisector, then you're equidistant from the sides of the angle. So I guess what that means is that if I pick a point, let's just put a point here on the angle bisector, let's call it point D, then that point D, which I can move around, is equidistant from the sides of the angle. So this gets into this question of, well, how do you measure distance from a point to a line? And you can imagine there are lots of different distances that you could measure here. If I put a point here, I could think of all of these as distances from a point to a line. But usually the way we specify it is we say that the distance from a point to a line is the smallest of those distances. And it turns out that the smallest of those distances happen when DE is perpendicular to AB. So in other words, when we measure perpendicularly from the line to the point, we get the shortest distance. So I hope that makes sense. So what we're going to do is we'll get rid of this point E, and we'll measure the perpendicular distance from D to each of the sides and see if it truly is are the same. So to do that, you have to develop a perpendicular line through D perpendicular to AB, and a perpendicular line here, which will allow us then to identify these 2 points. I'll hide the 2 perpendicular lines now, and draw in those 2 lines. And so now we can kind of see that it does indeed look like those 2 line segments are equal in length. We can actually see them over here on the left. Segment ED and FD are both 2.83 in length. And it doesn't depend, of course, on the size of the angle. Just to make this completely clear, let's go ahead and measure the distance from D to E. Oh, maybe not. Doesn't want to let me measure distance. Some sort of a weird glitch here going on. Let's try it one more time. There it goes. So now we can see those two distances. If I grab point A and move, we can sort of look at what those distances do. And it sure looks like when I'm on the angle bisector, I'm equidistant from the edges of the angle, or the rays, I guess, that define the angle. So that's the characterization of the angle bisector. Let's go ahead and prove that it's true. Okay, so we have two things to prove. This is a biconditional, so we have to prove it both ways. So let's go forward first. If a point is on the angle bisector, that point is equidistant from the sides of the angle. So let's see, let's go ahead and think about what would happen. We'd first put a point, let's call it P, on the angle bisector, and then we'd measure the distance from P to BC, so we'd measure that distance perpendicularly. Each one of those would have some meeting point. I think the way your book labels these are as X and Y. And what we're trying to show is that PX is equal to PI. I think it's pretty easy to see that we have an angle-angle side congruence here. Let's go ahead and mark the things that we know are congruent. We have a shared angle, or an equal angle here. We have a right angle there. And then both triangles share this side right here. And so the proof, and again, this is just a proof sketch. The proof sketch would be something like this. Triangle, let's see, PXB is congruent to triangle PYB by angle-angle side. So what do we get? We get that PX is equal to PY. So a quick angle-angle side triangle congruence gives us the result in the forward direction. Let's see how this looks in the reverse. Let's sort of split the page here. So how would it work here? So the reverse direction is if P is equidistant from AB and BC, then P is on the angle bisector. Let's see if that's true. Okay, so P is equidistant from AB, and that means that we are given, I should do this in black then, we're given that that side and that side are the same. We have a point that is the same distance from two sides of an angle. And what we want to show is that it's on the angle bisector. So let's go ahead and use blue to add to our drawing. I'll draw in this line. Actually, I don't need to draw the big long one. I think I just need to draw BP. Let's make it straight though. Okay, so I draw in BP, and now it becomes pretty clear that in the two triangles shown, they have a shared hypotenuse and a shared leg, and they're both in right triangle. So by hypotenuse leg, I'll use, let's say, a pink triangle. We have a hypotenuse and a leg in each triangle. which by the Pythagorean theorem guarantees then that the other leg would have to be congruent. And so in effect, what we have is side triangle congruence. But in right triangles, of course, we only need two sides congruent because the third side is forced by Pythagoras. So I think that's the argument. Once we have those two triangles congruent, of course, then what that does is lead to these angles being congruent. So that's the method of proof here. Let's see, what would we say? I guess the proof sketch would be something like this. Same story. We need to give these things labels X and Y, I guess. So we'd say that triangle PXB is congruent to triangle PYB by hypotenuse leg. So angle what? XBP not congruent but equal to angle YBP. So what? BP is the angle bisector of angle ABC. I hope that makes sense. They're just two quick proof, or I guess quick lines of reasoning of why the characterization of the angle bisector holds true. So let's move on and talk a little bit about the in-center, in radius, and the in-circle. It says that the three angle bisectors of a triangle are concurrent at a point, I, which is equidistant from the sides of the triangle. If we denote by R the distance from I to each of the three sides, then the circle of radius R centered at I is the unique circle inscribed in the given triangle. So this is the idea. I is what we call the in-center, and it's at the location where the angle bisectors meet. And we should be able to then create some sort of a circle that's inside the triangle. So different than the circumcenter, which has the circle that passes through the three vertices, usually exterior to the triangle. The in-center is the center of the circle that fits just perfectly within the interior of a triangle. Let's go to GeoGebra and look at that. I'll go ahead and what do I want to do? I want to get rid of everything. So let's see. How do I get rid of everything? I thought there was a quick, easy way to do with select all here. Select all, and then go ahead and delete. Okay, let's start with the triangle. Let's start with the angle bisectors next. So I'll do the angle bisector of angle A, of angle B, and angle C. And voila, the three of them do seem to agree. They meet at a point we call usually I. I'll rename it. Okay, so there's our point I. Get rid of this point E. I don't know how that got in. And kind of interesting just to see what happens. It does appear that that point always stays interior. to the triangle. And then we're told that that point is the center of a circle that fits perfectly inside. Now, to find the radius of the circle, we'd have to drop a perpendicular. So I'll create a perpendicular line perpendicular to this side passing through I, and I'll find its intersection with the side of the triangle. That wasn't the right one. Let's see here. There it is. So one thing to notice is that the angle bisector doesn't always meet the opposite side perpendicularly, but once we know that perpendicular distance, well, let's do it for all three sides. I'll drop a perpendicular to side BC next. So this side passing through A. Sometimes it's kind of hard to see which one is there. It's easier to see. So this one is the spot where we would have the perpendicular. So that would be a drop perpendicular as well. Let's drop a perpendicular finally to the last side. Oops. Oh, it doesn't like me. I'll pick this point, this side. There we go. Put a point there. Maybe. There it is. And add a segment. And then I'm going to hide my perpendicular line. So now we have, I guess the idea is that the point where the three angle bisectors intersect seems to be a new center of the triangle. And that center is unique in the fact that it creates a spot where all three of the distances from that point to the sides of the triangle are the same. Let's just make sure that that's the case. We'll go to the distance tool and see what that distance is, and that distance, and that distance. And sure enough, they are all the same, as the theorem says. And that means if they're all the same, I should be able to create a circle. I need to get rid of that guy out of my way. There we go. Should be able to create a circle centered at I with D as, or with any one of these as its radius. And that circle should then remain just perfectly inside of the triangle, tangent to all three sides of the triangle. And sure enough, that's the end circle. All right, let's go ahead and prove the statement. The three angle bisectors of a triangle are concurrent at a point, which is equidistant from the sides. So I'll do a proof sketch here. I'll just say let triangle ABC be considered. And we're going to let I be the point where the, let's say, bisectors of angle, let's pick B and C. Meet. Okay, so let's go ahead and draw that up. We'll have a triangle. Something like that, I guess. Okay, so the triangle is ABC. And we're saying that angles B and C are bisected. So we'll have something like, I don't know, something like that. Something like, I don't know, there, I guess. Which would make this point I. So we know that this angle and this angle are the same, and this angle and this angle are the same. Okay, got quite a racket going on here. So what it says, what we do next is from I, we're going to drop perpendiculars to each side of triangle ABC. Oops. As shown in, I'll do green here. So if I dropped a perpendicular to this side, it would maybe, oops, I'm going to do it in green. It would maybe look like that. If I drop a perpendicular to this side, it would look like that. If I dropped a perpendicular to this side, it would look like that. I'm going to let this point be V, this point be W, and this point be U. So if we drop perpendiculars to each of the sides, by our lemma we just proved, we get that IU is equal to IV, and IV is equal to IW. So why is that the case? Well, because we're on the angle bisector of B, or wait, I guess the angle bisector of C, right? We get IU equal to IV. I'll say angle bisector of angle C. And because we're on the angle bisector of B, angle bisector of angle B, right? But what you should notice is that what this gives us is that IW is then equal to IU, which then proves, again, I'll give it, I need another page here. I'll just erase that. So I'll say again, by lemma 2.24, this shows that I is on the angle bisector of angle A. I mean, just think about that, right? Since we're equidistant, IV is to IW, then we're equidistant from the sides AB and AC, which by our lemma means that we're on the angle bisector. Okay, so what have we shown? We've shown that the three angle bisectors okay, so we know they're concurrent. That's nice. And we also know that since they're all on the angle bisectors, and we've measured, I guess, the dropped perpendiculars, we know that they're equidistant from the three sides. So we know that, for example, that IU is perpendicular to BC. IV is going to be perpendicular to AC, and IW is perpendicular to AB. Okay, so that means that sides AB, AC, and BC are all tangent to a circle centered at I and with radius, we're going to call it little r, equal to, I don't know, any one of them. IU equal to IV equal to IW. So what have we shown now? We've shown that a circle with center I and radius R is inscribed in triangle ABC. The last thing we have to prove, if we go back to the lemma, is the fact that it's unique, right? And it's fairly quick to do that. Let's do that and end the video for now. I'll just say, let's shift colors again here just to, why don't we go purple? Is the circle unique? Well, let's see. Let's consider another circle inscribed in triangle ABC. So what would that look like? I guess you'd have something like, oh, sorry. I'm going to try to do this. We'll see if this works. Okay, make it a little bit bigger. Hey, I didn't do too bad. Okay, that's about as good as I can get it, but let's imagine that that circle actually is inscribed, does just barely touch the edges of the triangle. Let's go ahead and label this up, A, B, and C. Oh, I know what I'm doing wrong. Get my pen tool back. A, B, and C. Let's let sort of these points be the points at which the circle meets the side. He usually labels them X, Y, and Z. So it's going to have some center, and let's call it at P, and we'll know that if it's tangent to those sides, then PX and PY would be perpendicular. But by the fact that it's a circle, we know that this is the same, right? So since PX equal PY, P is on the angle bisector of angle C. And we can kind of play the same game. Say similarly, P is on the angle bisector of angle, I don't know, you pick it, angle B, because this distance will be the same, right? So that's our lemma, that's 2.24 giving us that. So what do we conclude? Well, if P is the spot where the two of the angle bisectors meet, then P has to be equal to I. So there indeed, for any inscribable circle inside of a triangle, the center of the circle has to be the end circle, or the end center, sorry. So there's only one end circle for a given triangle ABC. Okay, I think I'll end the video there, and when we come back, I'll take a look at some example problems.